the entire universe, there is only one known life form at the present time, which is us. But is it truly the only life that exists? Or is it just a part of the vast cosmic landscape? Imagine if there were a museum storing every form of life in the universe. What strange things would it hold? First, it would be the feasible conditions under the natural laws we know. The only way left is for us to delve into the Extraterrestrial Life Museum right now. To have hope of finding extraterrestrial life, we must know what we are looking for. We will start from somewhere and figure out how to narrow down these seemingly endless possibilities. One thing we know for sure is that nature plays by its own rules. No matter how alien life may be, it will be constrained by the same physical and chemical laws as we are now. Moreover, each extraterrestrial environment will shape what kind of life can evolve there. Yet, despite these natural barriers, there are possibilities that are hard for us to imagine. Trillions of planets out there, each a unique chemical cauldron pursuing its own complex evolutionary process. To guide this thought, the Extraterrestrial Life Museum will be divided into two places. Before we travel too deep into unfamiliar realms, let's ask ourselves, is life out there more similar to us than we think? SA factor connecting us to other species in this museum, it. Carbon is everywhere, one of the most common elements in the universe and well suited for forming large, stable molecules. This element has a rare ability to form four-way bonds with other elements and bond with itself in long, stable chains, forming large and complex molecules. This flexibility makes carbon the central part of life's molecular machinery. Carbon compounds we use have been found far beyond Earth, clinging to meteorites and drifting in molecular clouds. The building blocks of life drift like snow in the universe. And if extraterrestrial life chooses different carbon compounds for its biochemical structure, there are many possibilities to choose from. Scientists have recently discovered over 1 million alternative sequences to DNA, all based on carbon. If we discover other carbon-based life, fundamentally, we and they are connected. It's curious about life on these planets. If it can evolve, would it resemble our world on Earth today or be completely different? Some argue that, with the reasoning of convergent evolution, if conditions on other planets are similar to here, we would see similar life forms. The body parts of animals and plants look very familiar. On Earth, certain functions like vision, echolocation, and flight have evolved multiple times, independently in different species. This convergent evolution process also occurs on Earth-like planets, where organisms face similar environmental pressures. There's no guarantee, but there might be a certain universality to life. The greatest successes of evolution are repeating across the universe, each trait attuned for that environment. Bright planets would produce creatures with large eyes to capture more light, similar to nocturnal mammals. Some go so far as to suggest that humanoid creatures, human-like forms, would appear on other planets. T seem to stem from the same chain of events that created humans today, but we shouldn't. If just 1 in 100 trillion Earth-like planets produces humanoid beings, there could still be thousands like us out there. But in reality, we have many opportunities to study organisms in the same food chain. Such an evolutionary process is also widespread in plants. On Earth, plants are green because they absorb different wavelengths of light in the sun's spectrum. But stars emit many colors. So extraterrestrial plants would produce various pigments to adapt to the spectrum from their unique star. For example, plants receiving energy from hotter stars would be redder because they absorb more blue light energy. Or around dim red stars, plants would be dark. This adapts to absorb all visible light wavelengths. For Earth itself, plants might have once appeared purple due to a pigment called retinol, an early precursor to chlorophyll. Some think the simplicity of the retinol molecule would make it a more common pigment. Thus, we might see that purple is the preferred color of life. But the color of extraterrestrial plants isn't just that. We could also see those from many light years away with the naked eye. This species has a characteristic bulge under the light reflected from Earth. Searching for a similar prominent feature from another planet could point the way to extraterrestrial plants. This would be our first glimpse of life out there, a vibrant color radiating from a distant planet. But the most powerful influence doesn't come from the host star but from the planet itself. What happens when we change the planet's day length? What happens when we change the planet's tilt? What happens when we change the shape of the orbit? And what happens when we change the planet's gravity? Planets with long elliptical orbits will have sudden seasonal transitions. There could be planets that appear dead for thousands of years, then suddenly revive in spring. And most planets discovered so far are giant super-Earths. For example, Gliese 357d, 31 light-years from Earth, nearly 7 times Earth's size with a temperature of 53 degrees Celsius. How would life evolve on those planets? In the ocean, gravity is not a major issue. A planet with high gravity doesn't have strong gravity everywhere. If you're in the ocean, where all life began, you hardly feel gravity because your density matches the surrounding environment. It's when animals step onto land that they feel gravity. This strong force requires organisms to have large skeletons and muscles to suit complex terrestrial life. They also need a robust circulatory system, as plants could even be stunted due to energy consumption transporting fluids under stronger gravity. Planets with weak gravity are prone to atmospheric loss, lacking a magnetic field to protect them from micrometeoroids. But small planets could host secret oases with vast cave systems providing shelter for life. With more stable temperatures and protection from micrometeoroids, life could thrive underground on planets with deadly surfaces. The smallest habitable planet is estimated at about 2.5% of Earth's mass if terrestrial life evolves on such planets. Therefore, the smallest habitable planet is estimated at about 2.5% of Earth's mass if terrestrial life evolves on those planets. With more stable temperatures and protection from micrometeoroids, life could thrive underground on planets with deadly surfaces. With more stable temperatures and life could evolve underground on terrestrial planets. Therefore, the smallest habitable planet is estimated at about 2.5% of Earth's mass if terrestrial life evolves on those planets. With more stable temperatures and life could evolve underground on terrestrial planets. With more stable temperatures and life could evolve underground on terrestrial planets. Therefore, searching for the smallest extraterrestrial microorganisms would be a breakthrough development. Like stromatolites on Earth, biological layers can accumulate into massive mounds over time, leaving strange structures. When the numbers are large enough, some extraterrestrial bacteria could leave distinct biosignatures by releasing gases that wouldn't naturally coexist, like oxygen and methane. There are ways to produce oxygen and methane without life, but having them coexist in an atmosphere is nearly impossible. before the presence of biology to produce those gases on the surface, and it would leave a mark on the planet's spectral color. The next generation space telescope will search for such a sign on a planet not far from Earth. The nearest Sun-like star with an Earth-like planet, located in a habitable zone, is known to be 20 light-years away and visible to the naked eye. On the other hand, the universe has objects easier to target than small Earth-like planets, such as brown dwarfs. Most brown dwarfs are too hot to support life as we know it, but WISE 08550714 is a completely different case. This star is 7 light-years away, with temperatures from -50 to -13 degrees Celsius. All basic elements needed for life have been detected in its atmosphere. And in these clouds, some layers would provide ideal temperature and pressure for habitability. It can host planktonic organisms in the sky, kept aloft by wind turbulence. And with enough force, these winds could even support more complex life. So far, we've detected over 25 billion solitary brown dwarfs in our galaxy, and their size makes research easier. The first specimen we discover in the Museum of Life might not come from a planet at all. This raises an important question. What if we're looking in the wrong place? And what if nature has new ideas about life that we haven't considered? Life we don't know. Strange biochemical structures. Most of the universe is too cold or too hot for liquid water and the biochemistry supporting life as we know it. But in extreme cases, we must consider many possibilities to search for life outside the habitable zone, in places that seem extremely harsh to us. Strange environments will require strange biochemistry. And while no element matches the versatility of carbon, a contender emerges: silicon. At first glance, silicon seems similar to carbon. It also forms 4-dimensional bonds and is also common in the universe. But upon closer examination, those two elements are actually pseudo-life forms. Silicon bonds are weaker and not easy to form large complex elements. Nevertheless, they can withstand a wider temperature range, opening up other fascinating possibilities. Life based on silicon instead of carbon can withstand extremely cold temperatures. Thus, we have a new limit for strange life forms. If OC is present, silicon will crystallize into solid rock. To avoid this situation, silicon-based life should be limited to OC-free environments like the cold Titan, Saturn's moon. Its vast liquid containing lakes like methane and ethane can be ideal environments for silicon-based life or other advanced biochemical organisms. Without needing abundant light sources, life forms on planets like Titan could be chemosynthetic organisms. Harvesting energy by breaking down rocks, such life forms could have very slow metabolism and life cycles spanning millions of years. In fact, strange life doesn't only exist on icy planets. Planet Saturn A with temperatures around 1026 to 1526 degrees Celsius is one example. At high temperatures, strong silicon OC bonds become flexible and more reactive, activating more chemical dynamics. This has led to a bizarre hypothesis that silicon-based life forms are living in molten silica rock. In theory, those life forms could even exist beneath the Earth's crust, inside magma chambers as part of a dark biosphere. They are life forms beside us that we notice, even unaware of their existence here, including INA-based life, small enough to avoid detection by current equipment. Cosmic dust clouds and empty voids might be the last place you'd expect to find living organisms. Astrophysical plasma. But when cosmic dust contacts plasma, a type of ionized gas leads to something strange happening. In simulated dust particle conditions, it naturally organized itself into helical structures resembling DNA. Those plasma crystals even began exhibiting lifelike behavior, evolving into more stable structures and transmitting information. So can those crystals be considered living organisms? According to some researchers, they meet all conditions to be recognized as accidental life forms. So far we've only seen them in computer simulations. But some speculate we might find these crystals among ice particles in Uranus's rings. Plasma is the most common form of matter in the universe. If complex plasma crystals truly exist and if they can be considered life, this would be the most common life form. A hypothesis has been proposed. Could life be lurking in opposite environments, inside the cores of dead stars? When giant stars explode, some collapse into ultra-dense cores called neutron stars. Vast numbers of atomic particles packed together like sardines. Surface conditions are extremely abnormal, gravity 100 billion times stronger than Earth's, but beneath their iron nuclear crust something strange occurs. A hot, dense ocean of nuclei and subatomic particles. Stripped of electron shells, these nuclei would follow completely different chemical laws, not based on electromagnetic force, but the strong nuclear force binding nuclei together. In theory, these particles could bond together forming larger nuclei, then combine into even larger supernuclei. If so, this chaotic environment would mimic basic conditions for life. Heavy nuclear molecules floating in a complex particle ocean. Some scientists suggest unimaginably strange life forms drifting through the unusual particle ocean, living, evolving and dying on incomprehensibly fast timescales. We might not have the chance to detect such strange life sprouts, but could hope to find an even more extraordinary life form. Life isn't something that evolves naturally, it could be designed. And once intelligence is introduced into the evolutionary process, Pandora's box will be opened. Freed from typical biological limitations, life based on synthetic materials and machinery can be the most successful form of all. It could thrive almost anywhere, including the void of space. Opening up the ultimate, unprecedented frontier for biological life forms. Compared to the slow pace of natural selection, technological evolution allows for exponential growth, adaptability and resilience. According to some estimates, actively self-replicating machines can colonize the entire galaxy in as little as 1 million years. We cannot predict how super-intelligent life would organize itself. But in theory, there could be convergent evolution in the cosmos. The electronic properties of silicon could make it a common basis for machine intelligence. A salvation for our biological shortcomings. With all potential advantages, mechanical life could be the common endpoint. They will be the pinnacle of the evolutionary process. As the universe expands, domination will become more feasible. And natural biological life will be viewed as a strange ancient beginning. Perhaps we ourselves will lead this transformation. And then, the experiment on humanity will be just the first link in the chain of diverse life among galaxies. So far, we remain the only known creatures in the Museum of Life. To truly understand ourselves, we must know whether we are the only species. American anthropologist Lauren Ashley once said that one will never understand themselves until seeing the reflection from non-human eyes. One day, those eyes might belong to extraterrestrial intelligence. The sooner we break free from the narrow view of evolution, the sooner we can explore our origins and destiny. We have seen what can exist and know how to search for them. There's only one last thing to do: begin the search. Although knowing this path requires much time and effort, but with evidence and discoveries from scientists, finding even many other forms of life in this universe is entirely possible in the future. Whether that appearance is good or bad. What about your opinion? The comment section below the video is where we freely share and exchange. Don't forget to subscribe to the Dark Truth Files channel to accompany Primitive Universe. For now, goodbye and see you again. Subscribe to the Guia Amigo channel so you don't miss exciting videos.